Great. Well, welcome everybody to the first Stormwater 360 webinar of 2024. It's an absolute pleasure to have Johannes Bagali joining me to present this webinar. We're the team that brought you a webinar on the maintenance of storm filters towards the end of last year. And we're starting again this year with an overview of the hydraulics of proprietary treatment devices. As a company, Stormwater 360, we supply a range of treatment devices that all perform in different ways, but all rely directly on the hydraulics of the stormwater network and impact upon the hydraulics of the stormwater network to achieve the treatment outcomes. So it's a conversation that both myself and Johannes and the rest of our colleagues here at Stormwater 360, we have this conversation day in and day out with consultants, with designers, with contractors who put these in the ground. So we like to start off the webinar series with that kind of topic, covering the proprietary treatment devices. It's great to have all of you join us and devoting a lot of your time to this. The process is that we'll run through the presentation. There'll be a couple of polls during the presentation. The webinar will be recorded and you will have a link emailed out to you for that. If you have any questions, please put those in the chat part, and there's already been a question in the chat from Mervyn. So yes, Mervyn, the webinar will be recorded and you will get a link afterwards. We'll start off firstly with a poll. So Nicola, if you could bring up our first poll, and the question here is, have you designed a Stormwater 360 treatment device into your project? So just have a think of that, and when the poll pops up, give some feedback. So I'm going to say that yes, I have designed that. So it's great to see very high percentage of those that are coming that have done, and for those that haven't or haven't yet designed, hopefully this will answer some questions there. So we'll make a start then with the presentation, and it's the hydraulics of proprietary treatment devices really is a very important part of how we get our devices to work. So a little bit about the two presenters. I'm Matthew Howes, the Green Infrastructure Specialist at Stormwater 360. I sit within the sales team, so we'll be dealing with a lot of the immediate inquiries that come through. And Johannes, do you want to introduce yourself?
And hi, I'm Johannes, and I work in the engineering department of Stormwater 360. So I mostly design stormwater treatment devices to fit with the new stormwater network or stormwater line, and also considering some of the hydraulic implications it may have. So yeah.
So a little bit about the presentation, what we're going to cover today. So we'll start off by understanding the basic hydraulic principles. We'll define what driving head is. We'll define elevation head or physical drop through a device. We'll look at what headwater and tailwater are and how they impact both on the treatment device and how the treatment device impacts onto the network. We'll look at peak flows versus treatment flows and how we manage those large rainfall events, the likes of which New Zealand is currently getting a fair bit of. And then we'll look at the application of those hydraulic principles on the proprietary treatment devices, on the devices that we supply, and to show what the implications are and how that all fits together. And then we'll talk about how both Johannes and myself, how we think about a lot of these hydraulic ideas when we're providing a recommendation for a project. But to start off with, I always like to pose the question, why are we treating stormwater? Why are we putting these devices in the first place? A lot of the time, stormwater used to be about flood control. Ever since the Roman era, we've been getting water to go where it wants to go really well. But there's been a thinking shift, a paradigm shift in how we manage stormwater. And now it's about thinking about the ecosystem, providing both volume control and quality control. And this is the inside of a relatively typical storm filter. You can see here the amount of rubbish, the amount of sediment, polystyrene. There's all sorts of bits and pieces in here that without some form of structure to remove those contaminants from the water, that would get flushed straight to the receiving environment, straight to our rivers and estuaries up and down the country. So a structure, whether it is a manufactured treatment device or a pond or a wetland or something like that, is vitally important to protect our environment. We generally like to think about stormwater contaminants and categorize them, and that allows us to provide the right type of treatment device for that particular contaminant. And broadly speaking, we think about it in relation to the particle size of the contaminant. So oils and hydrocarbons, they sit slightly differently, but litter and trash is generally greater than 5 millimeters. Coarse sediment has a range of different sizes, but generally speaking, coarse sediment is anything that's 110 microns and up. So that's 0.1 millimeters and greater. Fine sediment, again, there is a range for fine sediment, but generally that has a median particle size of 75 micron, and it depends on the soil types of and the land use of the catchment as to what the particle size distribution of that sediment could be. For clay areas, it could be down to just a few micron that we need to remove from the stormwater runoff. We then have metals and nutrients, and they're particularly tricky because metals and nutrients can be both particulate and dissolved. So we need to think about those in a slightly different way. So for each of the different types of stormwater contaminants, there is a broadly accepted treatment outcome. And there is a range of treatment mechanisms and treatment devices that help achieve those outcomes. So for example, for trash capture, we use something like the litter trap, which is 100% trash capture at source. For things like dissolved metals and nutrients, and I encourage you to go and search out our nutrient webinar from I think last year or maybe the year before, where we discuss the ways and methods to remove phosphorus and nitrogen from stormwater runoff. This particular webinar will look primarily at the sediment component of stormwater runoff. So we'll look at coarse sediment, which we remove using a hydrodynamic separator or a GPT, and we'll look at fine sediment, and we'll focus primarily on the storm filter and the jellyfish. This allows us to think about stormwater treatment using a hydrodynamic separator that swirls the water around to remove the sediment, a cartridge media filtration device like the storm filter that passes the water through a media, and then a membrane filtration device like the jellyfish that passes the water through a membrane. So 3 different treatment devices, 3 different treatment mechanisms. And if you've got any questions about those devices, we'd be more than happy to answer them afterwards, or do go and search out our webinars on those topics later on. So water quality guidelines do exist in New Zealand. Every regional council has a water quality guideline, and then most district councils have a way of implementing that and device selections. They differ across the country, both in outcomes and approaches. So design in Auckland, say, might be different to the requirements for a design in Waikato or Christchurch or Central Otago. And what's quite key is that very few of these devices speak to the design and integration of a manufactured treatment device within a network. The Auckland Council's GDO1 document, for example, is how to design green infrastructure devices, how to design open source devices like swales, rain gardens, wetlands, and so on. So it's very important that we're thinking both about the treatment outcome, but also the hydraulics and the implementation of that device. And Kevin Jonathan, who helped me present this webinar last year, he's our lead technical engineer, and we wrote a paper on the hydraulic design of treatment devices, stormwater treatment devices, and how to make those designs resilient and the implications for thinking about those. So that paper is available on our website, and we can also send out the link to that paper. And it goes into an awful lot more detail than what we can in the scope of this short webinar, but it goes through and defines everything as needed. So with that, I'd love to pass over to Johannes, and Johannes is going to talk us through a lot of the technical considerations and definitions for that we're going to be talking about in this webinar.
Cool. Thank you, Matthew. As Matthew mentioned in this presentation, we'll be focusing on the fundamental hydraulic principles or considerations that we need to make when we design stormwater treatment devices. And most of you may be familiar with this concept, as typically designing a stormwater treatment device hydraulically is more or less similar to when you design stormwater reticulation systems or hydraulic structures. So we will start with the continuity equation, which describes the continuity of flow. And this describes flow equals velocity of the flow multiplied by the cross-sectional area of the flow. And the next concept is energy management, which this basically describes the energy upstream of, say, a hydraulic structure or a stormwater treatment device is equal to, the upstream, basically the upstream energy upstream of the device or hydraulic structure is the same as downstream with some additional head losses. And when we go into the next slide, we'll talk about the hydraulic gradient and Darcy's law. So the definition of hydraulic gradient is basically a change of a hydraulic head over a given distance or length. This is basically the slope of the water surface elevation between 2 points. And this can be calculated as shown in the diagram there. It can be calculated both vertically or horizontally. And when we come to the Darcy's law, the Darcy's law explains the flow of a fluid through a porous medium. And this can be calculated by, it says flow equals the hydraulic conductivity multiplied by the cross-sectional area and multiplied by the hydraulic gradient. So the Darcy's law explains that the flow is directly proportional to hydraulic conductivity, cross-sectional area, and the hydraulic gradient. So what that means is the higher the hydraulic conductivity, more flows you can discharge through a porous medium, and this can be applied in rain garden and also the filterer. I'm sure most of you are familiar with that product, and also the storm filter.
Right, it's nice seeing how the Darcy's law draws together, like the continuity equation and the head loss is all as part of one concept.
Yeah. And as Matthew just said, this is an application of the continuity of flow or the continuity equation. The only difference here you can see is there's an addition of the coefficient of discharge. And here you see an orifice, and the continuity equation can be used here. And in the next one, we have a weir as well, which is using the continuity equation with coefficient of discharge. So the main takeaway from this is that more head will result in more flow, and less head would result in less flow. Another consideration is head loss. So the head loss is the reduction of a hydraulic head when water flows through a system. So this can be a pipe, a channel, or stormwater treatment device. In this example, you can see water flowing through a hydraulic structure, and head losses can occur, for example, at an entry of a pipe or an exit of a pipe, or can be via a bend or obstruction of flows.
So there are a range of proprietary treatment devices that Stormwater 360 supply, and they are, broadly speaking, based around those different types of contaminants and treatment outcomes that we're looking at. And for this presentation, as I said, we're primarily going to focus on the cascade separator, the jellyfish, and the storm filter. Now, what's quite important to understand is that no resilient treatment device uses, there's no pumps. We don't use pumps. We use the gravity flow and the flow of the water to both start and provide the treatment mechanisms for all of our devices. So when we get approached for a design, that's why we do ask, what are the treatment requirements? What type of contaminants do we need to remove? what are the catchment areas and those flow rates? That helps the size of the device. But then we start asking about the available depth to invert for both the inlet and the outlet, if there's any constraints around head losses, and if there's any upstream and downstream water surface elevation constraints. So we're going to take the basic principles that Johannes has provided us, and then we're going to define each of those in detail and then relate that to our treatment devices.
Cool. So the elevation head is the physical drop between the inlet and outlet. So that would be the differential of the inlet and outlet inverse. It can be across a hydraulic structure or stormwater treatment device. And it is represented by delta Z, as you can see. That's the differential of the elevation between the inlet and the outlet. And this often is, as Matthew you would know, is often misinterpreted to be the total driving head, which isn't the case. And the total driving head is represented by delta H, which we'll be discussing about this further in some of the future slides. Yeah. And one important thing to consider is the misinterpretation between the physical drop or the elevation head and the driving head is that it can lead to underestimating the actual available driving head, and which can lead to some hydraulic issues upstream and sometimes cause flooding upstream. So it is important to consider this when we design a stormwater treatment device, and Matthew will be using some of our devices to explain this in a greater detail.
Yeah, I like to think of it as the structure might have the inlet and outlet at the same level, but if there's an orifice, say if you were putting an orifice on a stormwater tank to restrict the flow, that's obviously going to build up the water in a different manner to the fall through the device. So for the cascade separator, and we'll show you kind of where to look for this information on our drawings as well, we have the outlet invert and the inlet invert. And the idea behind the cascade separator is that we have the inlet and the outlet at the same level as much as possible. And ideally, there's no physical drop through a cascade, and that's the same for most of our gross pollutant traps. We had a couple of really good webinars on gross pollutant trap GPT hydrodynamic separator design that Mike Hanna presented last year that go into the reasons behind that. But the idea is that there is no physical drop through a cascade separator. Then for the jellyfish, so this is a jellyfish filter, and how a jellyfish filter works is, I'll show you on here. So water flows into the device, and then there is a maintenance access wall here that forces water down. Water level builds up behind that, comes down, and then pushes up through the pleated membrane cartridges and then out here. So with a jellyfish filter, you have an outlet invert level and you have an inlet, but it's range of inlets for the jellyfish. So the outlet and the inlet there can be a range of differences between the inlet and outlet on a jellyfish. And in fact, the jellyfish is a little bit special because as a treatment device, we can have up to 150 mil fall through the treatment device for the jellyfish, or we can have a bubble up system in the jellyfish where the inlet is actually lower than the outlet. And for the storm filter, we have our outlet invert here, and then we have the range of inlets where the inlet can go here. So from the storm filter, the standard manhole configuration, we have an outlet, and then the inlet ranges between 30 mil above the outlet invert to 770 millimeters above the outlet invert. So there is a range of inlet configurations that you can have for both the storm filter and the jellyfish. But it's really important to consider, and what we're going to discuss now, this is a separate measurement to the driving head requirements of all three of those treatment devices.
So the driving head is probably a term that you hear a lot since I believe most of you guys have designed Stormwater 360 devices before. So what the driving head is the measure of mechanical energy caused by flow. So when it travels through either a stormwater treatment device or a hydraulic structure, that is the mechanical energy required. So it is the differential of upstream and downstream water surface elevations across hydraulic structure or stormwater treatment device, and it's also known as a hydraulic head. Yeah, so the driving head is the water surface elevation required for a treatment device to operate as designed or to the designed flow rate. As Matthew just said, driving head is independent of the physical drops through a device. So the physical drop or the elevation head can be part of the total driving head, but the driving head by itself is the mechanical energy or the hydraulic head required to convey those treatment flow rates through a device. And a good example here is, as Matthew just explained earlier, the jellyfish system. Sometimes you can have a bubble up configuration through the jellyfish. So the driving head would still build up higher than the outlet invert. So it doesn't mean that you would have a negative driving head. So physical drop and the driving head are completely two different things.
So what does that look like for our devices? So for the cascade separator, because the inlet and outlet are at the same level, and there is a depth below the outlet invert, there is a permanent water level within the cascade separator. And the idea is that water flows in and then swirls around. There is a central swirl chamber, treatment chamber, where you have two opposing vortices, and then those vortices help both capture floatables and oils and trash, but that also helps settle out sediment. And with the cascade separator, we're achieving quite high removal percentages for coarse sediment, and then we're getting, broadly speaking, 50% TSS removal with a medium particle size of 75 micron. So we're getting an awful lot of the sediment that even the storm filter would provide treatment for with the cascade separator. As water flows in, it builds up behind the weir and within the internal components, and then comes down, up, and over the top of that weir to discharge to the outlet. So the water level that the water builds up behind that weir at the design treatment flow rate provides us with the driving head. So with the cascade separator, the driving head will vary based on the device size, the treatment flow rate, and even the pipe diameter, both in and out. It's much like sizing a weir in and of itself. Is the head losses across a weir will vary based on the flow and the geometry of that weir. So the minimum driving head is dictated by the weir height within the cascade, but it could be greater than that, and certainly if you're putting the peak flows through, would be a lot higher than that still. So the driving head on the cascade separator varies, and that's something that Johannes can calculate for you. For the jellyfish, again, there is a permanent water level in the jellyfish because there is a depth below outlet. So we have a sump, and that's where the cartridges sit. That's where the oil, the trash, the sediment is all captured into the base of that sump. So the driving head is shown on our drawings here, and as water flows in, it builds up to the driving head level, and then that provides the driving head. Now, with the jellyfish, it operates slightly differently. The jellyfish, the driving head is measured from the outlet invert and is typically controlled and limited by an upstream weir. Now, we'll cover offline design and diverting flows later on in the presentation, but with the jellyfish, the standard driving head is 457 millimeters. So that's the amount that the water needs to build up above the outlet pipe invert to operate at the design treatment flow rate. We can go down as low as 150 millimeters. And depending on the cartridge configuration, that might mean that we need to use more cartridges, because if we think back to the continuity equation, if we got the same amount of flow but going through smaller cartridges with smaller driving head, we're going to need more cartridges to treat that same flow. And with the jellyfish, the cartridge size and the driving head independently affect the treatment flow rate. So there's a lot of flexibility for design with the jellyfish. But of course, if you have an outlet invert level and an inlet invert level that ranges, that whether or not the fall through the jellyfish is 150 mil or less, you're still going to have between 150 and 457 mil of driving head. That water surface elevation behind that maintenance access wall still needs to build up to that point for the device to operate at the treatment flow rate. With the storm filter, so how the storm filter works is the driving head for the storm filter is dictated by the cartridge height that you choose. And what happens is water flows into the device. And as we covered quite neatly in our storm filter webinar last year, there's a float inside the cartridge, and then the water builds up to a certain point, and at that point, the priming depth of the filter, that float lifts and the treatment mechanism is activated. So there's no treatment flows up to that point. So the driving head of the storm filter is measured from the outlet level to the depth that the water will be inside the device before it A, starts operating, and then B, operates at that design treatment flow rate. So we have three different cartridge heights, the 69, the 46, and the 30 centimeter cartridges, and they have 770 mil, 540 mil, and 380 mil of driving head required for those to operate at the design treatment flow rates. So that means you can, with the storm filter, you can adjust the driving head just as with the jellyfish, and we just changed the height of cartridges to accommodate that. Of course, we said with the storm filter, we have the outlet invert, which is right at the base. There's very minimal depth below outlet for the storm filter, good for shallow sites. And there is a range of inlet levels that the inlet can go into the storm filter. So if you're using the 69 centimeter cartridge, you still need 770 mil of driving head, even if you've only got 30 millimeters of fall through that system. So the inlet configuration to outlet configuration is an independent measurement of the driving head. So what does that mean if we've got a lower fall through the device but a higher driving head? What does that mean for the upstream network? Well, Johannes is going to tell us that now.
So another consideration that we need to make when we design stormwater treatment devices is headwater, which is also known as backwater, which is a water surface elevation upstream of a hydraulic structure or a treatment device. And this can occur as a result of downstream obstruction or restriction that is typically used in a volume-based treatment devices, which relies on low fluid velocity for sedimentation. In this diagram, we see a hydrodynamic separator, which is called the vortex system. This system uses orifices and weirs to slow down the flows or the velocity of the flows.
Oh, apologies.
No problem. Which enhances the sedimentation or the settlement of the contaminants. And this is an important consideration we need to make, and we will see that in the next slide. Yeah, so in this diagram, you can see the delta Z, which we discussed earlier, which is the physical drop. And we have the delta H, which is the driving head. So the physical drop, which is the between inlet and outlet, is less than the driving head in this case, which this causes surcharging the upstream pipe or causing a headwater or backwater onto the upstream network. And this is really important to consider, obviously, because it will have an upstream network implication on the upstream network, and potentially, again, could cause flooding upstream. So it is important to consider this.
So I'm just going to pause before we talk about tailwater. Just want to, Nicola, if you can bring up our next poll. And the question for the next poll is, I'll let Nicola bring it up so I get the wording exactly right. Have you had to put a detention tank downstream of a storm filter or any of our other treatment devices? So I'm going to click yes. Quite a high percentage saying no, which is interesting if you've not had to work in a flow control area like a SMAF area in Auckland. But quite a few have done ponds and wetlands downstream, and looks to be kind of mid-30s have had to put tanks downstream. Certainly putting managing attenuation downstream and the effects of attenuation, which we'll cover here, is a key feature of a lot of the work that we do for brownfield, for infill sites, and redevelopment of existing catchment areas where the impervious area is being increased and we have to manage flow. So great to get a good snapshot. And for those of you who haven't had to put a detention tank downstream of a storm filter, fantastic. That's probably made your life a fair bit easier for that. So Johannes, tailwater, run us through what tailwater is.
Yeah. So we discussed earlier headwater, which is upstream of hydraulic structure or a treatment device. In this case, tailwater is the water surface elevation located downstream of hydraulic structure or a treatment device. So, which is a great question that we've asked. You know, when we use an attenuation downstream of a treatment device, in some cases there may be tailwater considerations that needs to be made. So there are two types of permanent and two types of tailwater. One is permanent and as one is operating tailwater, which operating tailwater means temporary. So that could be, for example, a dry pond where, you know, during the rainfall event can build up but slowly drains out. So that's not a permanent tailwater. And the permanent tailwater example could be a wet pond, which you always have a permanent water label, and that could have a permanent tailwater implication and on the upstream or on the treatment device or hydraulic structure. So it is important to consider where you look at the treatment device, and then also considering the tailwater impact it could have on the treatment device. So some of the implications are, you know, can affect the hydraulic driving head or the effective driving head, and also what the maximum treatment flow rate can be, which Matthew will discuss further.
So it's a very common thing for say housing developments where you'll have storm filters treating the access lots, and then you'll have detention tanks to attenuate the flows. So we're achieving either pre-development flows, 80% of pre-development flows, depends on the consent conditions and the requirements of the site. So what does that look like for the storm filter? So the storm filter, we said the driving head is measured from the outlet invert level. And that assumes free discharge of that pipe. So the driving head, the definition of the driving head is the difference in water surface elevation from the outlet invert level to the water inside the treatment bay where the cartridges are. And that is shown here. So 770 mil of driving head in this case. If there is tailwater from a structure downstream, whether that is a tank with extended detention, retention, or whether there's a pond, swale, or wetland downstream, if that surcharges the storm filter, that will reduce the effective driving head of the storm filter. Remember, we're thinking that the driving head is measured assuming a free draining discharge. So if there is tailwater, it reduces the effective driving head of the device. Although the water surface elevation within the device has been met, the floats will pop up and water will start flowing through. We don't have that full 770 mil of driving head to push the water through at the design flow rate. So what does that mean? Well, Johannes alluded to operationally, that means that we're likely to have a reduced treatment flow rate from a reduced effective driving head, which means the system will prematurely bypass. So stormwater treatment devices are sized to treat the water quality flows. Most places in the country, that is a rainfall intensity of 10 millimeters per hour. And in Christchurch, that's a rainfall intensity of 5 millimeters per hour. If there's tailwater and the system is going to prematurely bypass, that means that we won't be treating the flows of water that we expect to be treating. If we know this is going to be an issue, we can potentially accommodate this reduced flow rate per cartridge by adding in more cartridges. But it's something we'd like to try and avoid. Having tailwater in the storm filter is not how the device has been designed. The media has been designed for storm flows to get wet and to get dry. The treatment mechanism and how the device helps keep itself clean, and that's part of what we discussed in the designing for a BPO, best and a best management practice, is sediment wants to drop to the floor, and if sediment gets caught in the media, and if water backflows through the media, then we're kind of disrupting that. If there's prolonged saturation, so for example, if the storm filter media sits within an extended detention level, that can lead to biofouling and premature clogging of the media, which means you have to maintain the device that much more frequently. That being said, there are conditions, of course, for green infrastructure as well, it's quite a consideration to think about. Wetlands use the buildup of water to provide the treatment mechanism, but for other green infrastructure devices like the rain gardens or our Filtera, the hydraulic conductivity of the media, using Darcy's law as we discussed, is really important that the rain garden itself is free draining. So there is still a physical drop through a Filtera. There is still a driving head depending on the ponding level, and we still want to have offline design for that, for the rain garden or the green infrastructure device. And if there's tailwater that's sitting within the base of the green infrastructure device that hasn't been designed for, that means we're also reducing that effective driving head. Of course, bearing in mind that some rain gardens and green infrastructure devices are designed with a saturated zone for different types of nutrient removal, but that needs to be taken into consideration when you're doing the design. So for our Filtera, we still have a driving head, and the driving head is measured up to the ponding level, down to the outlet invert of the system. And again, that assumes free discharge of the pipe. So with the Filtera, if there is tailwater acting on the device, not only are we disrupting the media is not, and the biomass is not designed for lots of tailwater, we're also reducing the effective driving head of the system. So from the surface, it looks like the device is operating, the ponding depth has been met, but we don't have that full 915 millimeters of effective driving head. So how can we design to manage tailwater?
So ideally, when we design, ideally there will not be tailwater acting on a treatment device, as Matthew explained. It reduces the effective driving head. It can have also maintenance issues. So when we design, even it is temporary or tailwater, that's also discouraged. What we can do is, if we have a tailwater level, what we can do is raising that outlet level from the treatment device, for example, to avoid that tailwater. And ideally, that tailwater will not be affect the treatment device, at least in the water quality flows, or at least up to the 2-year storm event. And also considering what the drain downtime would be for the tailwater as well would be essential on how that would have implication on the treatment device in terms of maintenance.
Yeah. So it's something that we're very cognizant of the fact that many sites are severely limited, either because the infrastructure that a site is connecting into is particularly shallow, or the site itself is very flat and there are limitations. So we are absolutely able to work within those, but we do have some guidelines with which we have to operate, and Johannes can review those for you. But I'll cover a couple of options for how you can help minimize tailwater onto the storm filter. So working backwards up the system, you have a discharge invert, and that is typically set by the council connection that you have to connect into. Some sort of detention tank. So a surprising number of you haven't had to design detention tanks downstream of storm filters, but you'll be fully equipped to know how to deal with them for when that does pop up. We have a storm filter and then a catch pit. So as the storm filter has a driving head, and we said that's 770 mil, and that is measured from the outlet invert to the water surface elevation within the device for that to operate at the design treatment flow rate. So in this scenario, as water enters the storm filter and gets treated, it discharges into the tank, and then the tank restricts the flow, tains the water so it can be released in a controlled manner. But that then builds up water level inside the tank, which then acts upon the storm filter and reduces the effective driving head of the storm filter, as we've discussed. So there are a couple of options. You can either lower the tank, lower the discharge invert, but oftentimes it's not quite that simple, unfortunately. So the first option is to lower the tank, change the tank design. Can we design our cells and to avoid the problem entirely? Where that's not practical, though, the second option, as Johannes mentioned, is to raise the storm filter. And that can mean either by, instead of having the full 770 mil drop through the storm filter, is that we reduce that, say, down to 100, 150, even as low as 30 mil fall through the storm filter, and then temporarily surcharge the upstream network to accommodate that. But it is quite important that when we do that, that we do think about the upstream network as well. Just as the tank design of upstream of that affects the storm filter, so the storm filter upstream of that affects the network. And there may be minimum freeboard requirements that we have to consider and design for. So it's important that we get all of that information to give you as best design as possible.
So the next consideration is peak flows. So it is important to understand, typically stormwater treatment devices are designed to treat stormwater water quality flows and not peak flows. And you put the treatment devices in a stormwater network, and the treatment device is designed to treat the water quality flows, but actually the stormwater line or the network may be designed to, for example, to convey the 10-year flows or up to 100 years flows. And therefore, the peak flows have implication in some aspects. Firstly, when you convey the peak flows through the treatment device, one of the implications is you incur a significant hair loss, depending on how high the peak flow is, and that could affect, so we see the upstream network, as Matthew just mentioned. We got to check how that affects the upstream network, or with if we have enough freeboard to accommodate that. And another risks with conveying the peak flows through the treatment device is there's a risk of resuspension of sediments that has been captured previously. So again, depending how high that peak flow is, it could create a turbulence in the treatment device and then resuspending the sediment and potentially losing some of the sediment that we already captured. Another one is in some extreme peak flows, you could damage the internal components of the device. And in biofiltration devices, you could scour the media by conveying the peak flows through the treatment device. And therefore, it is important how we convey the peak flows around the treatment system.
To give you some context for that, at the moment we're working on a number of projects where the peak flows are 1.5–2 meters cubed per second. And the thought of putting 1.5 meters cubed per second through a treatment device when that's the peak flow, it is quite a scary thought, and could cause a lot of issues for the upstream pipe network that is being replaced and managed. So that's why we think about this quite a lot.
So what we can do to avoid these risks, or to minimize these risks, is we can do an offline design. So an online design is if you place in the treatment device, when you place it in the stormwater network, and the peak flows are also routed through the treatment chamber, that's an online design. And an offline design is bypassing those peak flows around the treatment system. So that can be done, for example, using an upstream diversion manhole. So only the water quality flows will be directed to the treatment device, and any flows that are in excess of the water quality flows then will bypass the system. This is considered best practice for all stormwater treatment devices, not just Stormwater 360. And that is because of it achieves the best environmental outcome, as you retain the sediments you already captured, and also you reduce the risk of any potential damage to the device. In some councils, offline design is required, for example, in Auckland. Again, what that means is only what goes through the treatment device, the peak flows bypass around the system. And yeah, so in Auckland, all proprietary devices are required to be offline. And offline design also provides a solution for very shallow sites. As you know, routing the peak flows through the treatment system, as we mentioned earlier, it results in higher head losses, which affects the upstream network. So if your site is already shallow, that's probably not the best way to go about it. So what you can do is you can use an upstream weir to divert those peak flows around the system, and you know, you can use, for example, a longer weir to reduce the head loss, and that way you can accommodate that in your shallow site. Yeah.
So what does this look like in practice again? So if we think about the offline design, this is a typical offline configuration. So we have a receiving manhole that sits on the main stormwater line. We have the treatment device, and whether that's a hydrodynamic separator, a jellyfish, or a storm filter, that sits off to the side. And then there is a weir that sits in the receiving manhole that diverts the flow first to the treatment device, and then that weir is set at the driving head level of the treatment device that's downstream. So then once the water reaches to the driving head level, we know that the device is operating at the design treatment flow rate, and so that all additional flows can go straight over that weir and bypass. So it's very important, as Johannes said, is that you can design that weir accordingly. So the overflow structures, all treatment devices have overflow structures within them as part of it, but it's designed as an overflow rather than a peak flow bypass. And the head losses across a diversion weir are going to be that much less because it's that much longer than a small overflow baffle structure. So that's quite important. So what does that look like in cross section if we think about kind of how the hydraulics work? So here we have a cross section, we have a jellyfish. So we have that receiving manhole that sits on the main stormwater network. We have the jellyfish that sits off to the side. The jellyfish, remember, has no more than 150 mil fall through the device. So we've got very small delta H, but the driving head level is going to be that much higher than the fall through the device. So as it starts to rain and water flows into the system, it preferentially flows to the treatment device, and then the water level within the treatment device builds up until we reach the design driving head level. So with the jellyfish, that might be, say, 150 mil, 475 mil. With the storm filter, that could be 770 mil. Any flows in excess of that then can overtop that weir in the diversion structure, and we prevent those high velocity peak flows going to the treatment device. So that's a typical offline design, but a product like the storm filter, we're able to provide that within one structure. So instead of having, say, 3 manholes for the smaller units and for some of the vaults, we can provide that within one manhole. The advantage of that is, although the manhole size might be larger, so for example, a single storm filter cartridge we can supply in a 1050 manhole. With the peak flow diversion, that needs to be supplied within 1200, but a 1200 manhole is still going to be more economical and easier to fit in tight sites where you've got service clashes to manage than to have 3 manholes with a diversion structure. So what does that look like? How do we manage that with the storm filter? Well, we still have that receiving chamber. We still have the treatment chamber, and they're separated by an internal baffle. So there's an actual separation there between where the peak flows are and where the treatment flows are. And then there is a diversion weir that sits across there. So that diversion weir, again, is much longer than, say, what an overflow and with the floatables baffle would be within a standard storm filter design. So you can see here is that we're still routing the flows around and past the treatment chamber during those peak events. So that's offline design, and that's good practice. And so to kind of wrap this all together, because we've kind of covered a lot of the kind of principles and how that applies to our devices, we try and help with as much as we can with all of these questions through that design process. The hydraulics of manufactured treatment devices aren't typically considered as part of the regional and district council guidelines, and some product approvals have information around hydraulics. Some product approvals don't have information around hydraulics. So it's really important to understand how the product that you're putting into your stormwater network is operating to avoid the issues that we've discussed. So we will ask you for the treatment requirements. Does it need to be a litter trap? Is it a cascade? Is it pre-treatment before a wetland? Or is it that full fine filtration? So we go down the storm filter or the jellyfish route. We'll ask for the catchment areas and the flow rates. Catchment areas and the flow rates helps us size the device, but also provide some insight into those peak flows and the head losses through that device, both at the water quality flow rates and the 10-year flow rates. We'll ask you for the available depth to invert, and the depth to invert is quite important. That's the depth from the surface to the outlet invert level. We'll ask you if there's any driving head constraints, and of course, driving head constraints. Driving head is different to depth to invert, is different to fall through the device. So there's 3 separate measurements that we will all ask for, and it's important that we think about those differently. We'll also ask if there's any downstream water levels, if there's a swale or a pond or a detention tank that we're discharging into. And then within all of that information, we can gather that together and we can provide a design recommendation for your site. We do have an online design tool. The online design tool is really useful to get a quick sizing and an idea of the rough size of devices, but it simply can't have the same level of detail and the level of customizability and options that we have available as if you approach us directly. So by all means, please do go on and use that online design tool. It will give you a rough idea of the size jellyfish, storm filter, or filtera that you need. But then send that information through to us and we can take a look at that and review that. So as we review the presentation and just cover off again the topics that we've covered, Nicola's going to bring up another poll, and it's just topics of ideas for future webinars that you might be interested in. It's always very nice to see how popular the hydraulics webinar is, but interested in what other information that you are keen to hear about. So for this presentation, for this webinar, we've covered the basics of the hydraulic principles. We've covered what driving head is, elevation head, and the difference between the two. Elevation head is the fall through the device, the difference between inlet and outlet, and the driving head is the difference in water surface elevation for that treatment device to operate at its design flow rate. We've discussed what headwater is and tailwater is and how that impacts both on the treatment device and how the treatment device impacts on the rest of the network. And we've discussed peak flows versus treatment flows and how that all applies when we're designing our Stormwater 360 treatment devices. The main takeaway through all of this is do come to us and ask us for our help. We are here to help. It's in everyone's best interests that we provide as good solution as we can, both for the project from an economics perspective, but also for the environment and meeting the environmental outcomes. So if there are any questions from this, I'll take a look at the chat function now to see what questions there are. But if there are any questions, please do put them in the chat function and we can take a look at that. So at the moment, lots of people are typing in responses into the poll. Let's see if there's any other questions? While we wait for that to come through, I guess I'll start us off, Johannes. Johannes, in terms of the hydraulics and things that we often have to look at the most, I guess what's the one biggest question that we either get asked or have to respond to as part of the design for, let's say, when we're designing and around the hydraulics? What would you say?
Definitely has to be the driving head. So the confusion between driving head and physical drop. which is a really important question and it's a very valid question. But yeah, that's that differential between the physical drop and the driving head. As we discussed earlier, the driving head is the mechanical energy or the hydraulic head required for the treatment device to operate as designed, whereas the physical drop is, you know, the differential between inlet and outlet. And in some cases we get asked, you know, do we need to specifically have, for example, the storm filter 770 between an inlet and outlet? And as you explained earlier, we don't need to because the cartridge or the system would build up by itself. So it is the water surface elevation difference between upstream and downstream water surface elevations, whereas physical drop is between inlet and outlet. But yeah, I would say that's probably the most question I get a lot.
Yeah, and I guess if we do get approached with a site that is particularly shallow and complex, what's the process that we would go through with the consultant, with the engineer, to come up with a solution? Come up with a solution for a particularly shallow site? Is there like a range of questions that we might ask? What might we kind of go through for a shallow site?
Yeah, definitely fully understanding what the site constraints are. For example, how much depth you have. It can be, you know, what is the outlet, you know, what is the level of the shallowest catch pit upstream, which typically is the case in Christchurch where it is quite shallow. And in that case, once we know that, then we can recommend a device or a cartridge, for example. We can use a shallow cartridge to accommodate that constraint.
Ben's asked an interesting question here, and so he's asked about, is there a summary of driving head and flows for some devices? So it's an interesting one, and there is information, Ben, on our website and in our brochures around the driving head requirements for the devices, and especially for storm filters. You know, we have those three driving head options based on the cartridge height that you choose. And of course, flow rates is a little bit different because the flow rate for a particular cartridge will be different depending on the depth that you choose. And so we adjust the number of cartridges that you need based on the treatment flows and the requirements for there. So we can certainly send you through that information. It's also on our website and on the product sheet. But if there's any further questions, there's more detail in related to a particular project, then absolutely send that through, and Johannes or myself can take a look at that for you. Here we go. Another question from Simon. What do you do if there's restrictive tailwater but cannot elevate the treatment device? I.e., it's a permanently flooded scenario, thinking especially in Christchurch. Simon, I wonder if you are if you're based in Christchurch, then Christchurch is a particularly challenging site or challenging city to provide treatment designs in. The entire city is mere meters above sea level. And in that instance, that's when I would generally defer to a great colleague, Anton Carr. Anton has spent a great number of years providing treatment solutions for the Christchurch area. A lot of the time, I guess, Johannes, we do see some pumped designs for treatment. Of course, key for pumped designs is that we only pump the treatment flows, and then the rest of the area, the rest of the flows are gravity fed. Other solutions would be maybe we can't make the storm filter work, because even though the storm filter we can get to around a minimum of say 800 millimeters depth to outlet invert from the surface. Yeah. But if we can't make 800 millimeters work, then maybe we look at using a different system, a non-trafficable system where we bring it right up and potentially sometimes have the top of the treatment device sticking out of the ground. It very much in those instances, we would look to design you something that is best suited for that site. So whether it's either providing a pumped solution in some cases, if that is acceptable for that project, or by changing the type of treatment device or the configuration of the treatment device, all allows us to manage restrictive tailwater level. And of course, if there's a permanently flooded scenario, then we'd have to take that into account when thinking about the hydraulics of the treatment device and designing it to match those flow rates. Great. Well, look, thank you all for joining us today for this webinar on the hydraulics of proprietary treatment devices. It's been great to have so many people join us and so many great ideas for the future webinar topics in the poll. So we'll definitely take those on board and look to bring information about that. If there's any further questions, then don't hesitate to get in touch with us. We are here and available and always happy to talk through these topics with you and specifically how they might apply to your project. So it's thank you from me and
yeah, thank you so much for the questions and the polls as well. Yeah, if you have any other questions, you can directly contact us as well, and we always here to help with the design. And yeah, review the drawings or recommend what would solve the site constraint that you have. So we always here to help.
Brilliant, and we'll leave that all there. Thank you very much. See you for the next webinar.